Hello everyone and welcome to the GPT Industries webinar, Is Flange Corrosion an Isolated Issue? Brought to you in association with Oil Review Middle East, the leading oil and gas magazine for the Middle East and North Africa. I'm Louise Waters, editor of Oil Review Middle East, and I'm delighted to be moderating this webinar today. And I do hope you're all keeping safe and well. By way of introduction, GPT Industries, a division of Enpro Industries, is the industry-leading manufacturer of critical pipeline sealing and electrical isolation products with a focus on safety, performance and reliability. They employ advanced engineering and manufacturing processes to meet the challenging demands of oil and gas, wastewater, and construction and infrastructure industries. So to our subject of our webinar today. The pipeline industry has changed tremendously over the past 75 years, as we're going to hear. New exotic metallurgies have been introduced to further resist the aggressive media and chemicals that are now often found in oil and gas streams, such as sour gas, chlorides, and steam. Pressures and temperatures have increased, and emissions reduction requirements have become a way of life for most companies. Meanwhile, the operation of a fire-safe pipeline has also become a higher priority. So, how are changing pipeline conditions affecting flange management in the MENA region? And how effective are traditional isolation solutions in coping with these increasing demands? Are they fit for purpose? These issues will be addressed at our webinar today. We'll also be covering safety and environment considerations of fires, leaks, emissions, and other factors contributing to flange corrosion, and hear about advancements in isolation systems and technologies that support the mitigation of pipeline corrosion. And in particular, we'll be hearing about a new technology from GPT Industries, which has been designed to address all the challenges that we'll hear about today. Sadly, GPT Industries' Robert Colton, Director of Europe, Middle East and Africa, who was to have been presenting today, is unable to do so due to a family bereavement. Our thoughts are with him. So Rony Roy, Senior Applications Engineer at GPT Industries, who is in any case going to be joining us for the Q&A, will be giving his presentation in his place. Rony has been working as an applications engineer with GPT for 7 years to give technical support in the Middle East, Africa and India. Prior to joining GPT, he was working as a project engineer in an EPC company and has been associated with the oil and gas sector for more than 10 years. Rony is a Bachelor of Engineering from the Institution of Engineers in India and also a certified chartered engineer. He's been responsible for conducting GPT engineering activities such as drafting specification for isolation products in the regions, assisting leading oil and gas customers by conducting seminars and webinars on the need for isolation products and their significance in flange corrosion. Following the presentation, Rony will take questions. So please do get those questions coming in so we can get a good discussion going. You can submit questions in the Q&A chat box below your screens at any time throughout the presentation and afterwards. So over to you, Rony.
Thank you, Louise. Yeah. Good afternoon and welcome everyone to this presentation. We from GPT Industries are very happy to bring this topic to you all. Before we begin, I hope you and your families and everyone is keeping safe during these times of disease all around. But and as safety measures, I would just like to go through that you are self-isolating yourself as well as taking care of personal hygiene, hand wash, and all those things. As we move on to this topic, the topic today is flange corrosion, an isolated issue, and we are happy to bring this topic to you. So, as Louis was introducing to us, the pipeline industry has changed tremendously over the past 75 years. And new exotic metallurgies have been introduced to further resist the aggressive media and chemicals that are now often found in oil and gas streams, such as sour gas, chlorides, and steam. Even pressures and temperatures have increased, and emissions reduction requirements have become a way of life for most companies. Meanwhile, the operations of a fire-safe pipeline has also become a high safety priority. Today, we will look into these changing and demanding conditions that are driving the innovation in this industry, and also dive into how these challenges are affecting flange corrosion and how do you overcome them. So the agenda for today's presentation is the changing pipeline conditions in this region, the resulting effects on flange corrosion and how to mitigate it, our traditional isolation solutions equipped to meet the ever increasing challenges. And then we will look into some live cases, a future ready solution, and how does current and new technology fare in the live examples and existing conditions. Today we are standing at the threshold of a significant energy revolution that is going to change the way we live, travel, conduct business, and manufacture. Yet we know that man's dependence on hydrocarbons are not going away anywhere soon. In fact, peak oil is still a couple of decades away, and gas continues to dominate the market as it backs up renewables and provides cleaner energy. Population growth is also driving that demand, and producers are going to have to operate differently to meet it. The easy to extract fields are getting depleted. As an attempt to make the supplies meet the demands, newer techniques and technologies are required. Now the conditions are changing because the scenario is becoming more and more demanding for oil and gas or hydrocarbon industry to rejuvenate old wells and to go deeper than ever before to obtain the oil and gas. Enhanced oil recovery methods have to be put in place now using steam, nitrogen, natural gas, carbon dioxide, thermal injection, and these are all on the rise and will continue for the next couple of decades. This exposes products in the pipeline to temperatures and pressures and mediums that it has never seen before, and that too in large quantities. High pressure and high temperature wells and ultra high pressure and high temperature requirements are on the rise. Suitable materials that can withstand very high temperatures and very high pressures are required to be employed for each and every component in a pipeline. Further, the conditions are changing in terms of the sour content in the wells. As mentioned earlier, the easily recoverable and sweeter resource wells are getting depleted quickly. The newer enhanced recovery methods and knowledge in exotic metallurgy has helped to drill deeper and extract from wells with more sour content. H2S from these sour wells, H2S or hydrogen sulfide, affects detrimentally on all the components used in these operations. In pipelines, hydrogen sulfide is a primary contributor to a substance called iron sulfide, which you see as black sedimentary buildup inside the pipelines when you open it up after certain years for maintenance. And this buildup is intrusive in nature, and it disturbs the flow of media and even facilitates corrosion. As you can see from this global map, the black dots are the sour wells around the world, and all the sour wells are about higher than 10% of H2S content. Even the greenhouse effects, greenhouse requirements, reduction requirements are also in place with government entities taking a much more proactive role to bring the emissions down. Talking about onshore, offshore refineries, distribution lines on each and in the upstream, midstream, and downstream processes of the hydrocarbon industry, every sector is aiming to reduce the carbon footprint and the emissions. Shell is aiming to reduce its carbon footprint by 20% by 2035. That's like 15 years down the lane, where everyone is concerned about reducing the emissions. Even here in the Middle East, local players are the end users here are adopting serious measures to reduce their carbon footprint and be less taxing on the environment, which is a good news for everyone, and manufacturers like us also required to be aligned with it for a joint effort to a good cause. ADNOC recently mentioned that it aims to reduce its carbon footprint by 10% by 2025 and 2023 and 25% by 2030. And to achieve this, ADNOC is constructing new carbon capture, utilization, and storage facilities alongside the existing Al Riyadh one. So, and Saudi Arabia's state oil giant, Saudi Aramco, has agreed to reduce the carbon intensity of its business as part of the Oil and Gas Climate Initiative, which includes Shell, BP, and ExxonMobil as an industry-funded alliance. They have pledged to reduce the carbon intensity of their fossil fuel production to between 20 and 21 kilograms of carbon dioxide per barrel of crude by 2025. To meet these stringent emission norms and targets, the ceiling needs to be more tighter, with little to no chance for permeation. So how does these conditions influence sealing? Such changing conditions requires a significant improvement in flange joint sealing, and it is the need of the hour, as only a correct seal or gasket can only allow to keep the stuff that should remain within the pipeline within the system. The ideal seal should be able to, as you can see from the slide, should be able to remove the chances of contaminating the surrounding environment with a tighter seal. The material themselves being more compliant to the conditions will help in reducing toxic emissions and better performance. A proactive method of prevention of seal failure by increasing the skills of personnel through training and doing the installation correctly at the first place is also required. Better and safer seal design to eliminate risk during emergencies such as fire. All these are part of contributing to the, all these factors are contributing to the requirement of bringing down the emissions and making the seals more effective in the future. With all this insight in developing the ultimate seal for future, we will see how seals and different conditions such as environmental and metallurgical factors can affect the flanges where they need to seal. Flange face corrosion is a subject in its own rights, as many companies have invested millions of dollars to ensure the flange joint conditions perform well to meet production consistency and quality, along with increasing its life and reliability over the years. Corrosion preventive measures such as regular maintenance and using flange isolation kits and using flange joint covering bands are some of the methods adopted for achieving this corrosion against flange joints. Today we'll look into how flange isolation kits contribute to this requirement. So what does a flange isolation kit do? As you can see in this slide, there are 5 different activities that or 5 different targets that can be achieved by using a flange isolation kit. The first and foremost is the galvanic corrosion. When 2 dissimilar metals of different electrical potential are coupled with each other by a metallic path and in the presence of an electrolytic or conductive media, it will lead to galvanic corrosion. As you can see in the first image here, one of the flanges have corroded very badly, and this is a typical example of galvanic corrosion. The badly corroded flange has a metallurgy that is more anodic in nature and acts as a sacrificial metal here. Flange isolation kits remove the metal contact between such flanges at the flange faces with an isolation gasket, at the studs with an isolating sleeve, and at the nuts with isolating washers, as you saw in the previous slide. By isolating the metal-to-metal contact, flange isolation kits eliminate any chance of galvanic corrosion, and so preventing such kind of flange reduction or material reduction in the flange joints. Sorry. In the second example, you can see, or the second use, you can see flange isolation kits are designed to match the flange bore, whether it is a raised face flange or a ring type joint flange. This would stop cavitation and flange erosion, which keeps electrolytes from the flange face, stopping flange face corrosion and internal crevice corrosion. This also would not have provided an area for microbial growth and microbially induced corrosion, since the flange isolation gaskets are not are designed as a type F or a ring type or a ring kind of design, which begins from the bore of the flange until the PCD ID of the nuts of the bolts. The fluid trap area in an ring type joint, flange joint with ring type gaskets are also eliminated by this kind of arrangement, and chances of sedimentary buildup that generally occurs between the groove that is inboard of the flanges and the bore of the actual bore of the flange can be eliminated by using a flange isolation kit or a gasket. Also, for the same reason that we mentioned just now, flange isolation kits, since they are made as in one design for both raised face and ring type joint flanges, you can use it to seal both raised face to raised face configuration, ring type joint to ring type joint flange configuration, or even a raised face to ring type joint flange configuration, because it is a similar design that goes in any kind of configuration. So this is not very regular, but sometimes in the industry or in the sites, it ends up with such kind of an arrangement where a valve has been delivered with a raised face and the line has got a ring type flange on it, and you need to seal between them. So this gasket, the flange isolation gasket, can help you sort out such kind of an anomaly. Another benefit is that flange isolation kits require much less load than a ring type joint gasket. So flange stress gets dramatically reduced, leading further to reduced potential for stress corrosion cracking in the wells. Any component, whether it is material or human beings, once it is under stress, they are bound to crack, or they are bound to break. So it is better to keep things under less stress. And the final one is isolation joints being used in CP system or cathodic protection systems. This enables isolation between sections that are CP protected and unprotected. And it also helps to isolate, it also helps to increase the CP cathodic protection efficiency by eliminating the risk of stray currents and surrounding electrical influence. Also, it is used in long pipelines at sections of above ground and underground transfer points. So we have seen what a flange isolation gasket kit does. Now, where do we stand in terms of this industry? Let us see where does the current technology stand and why innovation is long overdue in this field. If we look at the changes in isolation gasket industry, as pipeline conditions have changed, we can witness significant growth and innovation as compared to other sealing solutions throughout the 20th century. As you can see in this graph, you can follow the changes step by step, and the step-by-step innovations that has been going on in this sector. In the beginning of the last century, phenolics was the material of choice, which was then taken over by fiberglass or glass reinforced epoxy that came into the scenario through development in material science in 1942. Over the years, since its introduction in the isolation industry, the glass reinforced epoxy has seen various improvements, or gaskets made from the glass reinforced epoxy has seen various improvements, and incremental development to compensate it for its shortcomings and the heavier demands of the hydrocarbon industry. Various improvements in the design of the isolation gasket made by GRE were ushered in to make it withstand high pressure, provide fire safety, and make it more chemically compatible. Yet we see a common theme here. The glass reinforced epoxy has its own demerits, and gaskets laminated with them have isolated flanges but have struggled to keep up in other areas. Permeation, susceptibility to melting in a fire, chemical incompatibility, all these issues have plagued the plastic laminate or the glass reinforced epoxy laminate that goes on top of isolation gaskets. Now, what is the challenge with the current technology? We have seen designs where the isolation gasket is made from a stainless steel or a metal core, which is laminated by GRE or glass reinforced epoxy on both sides of the gasket. As a global manufacturer, GPT always interacts with corrosion engineers, integrity engineers, reliability engineers, and material engineers at our end user companies throughout the world. And we perform voice of the customer interviews regularly. In such discussions, we come to know the trending changes and new needs of the industry and design our products accordingly. During such interaction, one of the engineers of an esteemed customer once quoted, "I really like this gasket that you have invented, but this has a leak to seal design." And he was right. As you can see in this picture here, he was referring to the VCS gasket, which is being shown between two flanges. A portion of it is shown in between two flanges. Now the VCS gasket has got a 316L SS core metal, and it has got glass reinforced epoxy laminates as part of the retainers, laminated on top of it and on both sides of it. And it has got a groove where a Teflon seal gasket, which is pressure energized or spring energized, laid in board. Now, when the pressure is introduced into the media, into the line by the media can permeate through the GRE material, the glass reinforced epoxy material, and can reach the Teflon seals. Now, the Teflon seals are designed in such a way that it compensates for this shortcoming, and it positively gets energized, further pressing against the flange face and providing a positive sealing effect. But if we want to face the future requirements like lower emissions and better sealing capacity and a tighter seal, we need to eliminate this kind of a sealing technology. The reason behind the above statement is that when we install this gasket, the media that permeates through the GRE, in the case of an H2S or steam, will become more and more susceptible to failure, and it will be a challenging situation. Now, talking about the GRE permeation, these are some lab images that we had created over the years to show how a GRE fails. GRE fibers act like straws, and they can give a straight or a very continuous path for media to flow through them. And you can see there is another picture at the right hand side. It is a gasket that was taken out of operation after 15 years in a highly viscous hydrocarbon line, and yet you can see the hydrocarbon or the media had permeated through the GRE body itself. Now, moving on to live cases that has led us to think about these kind of failures is one of them is here, where the size was a 12-inch 1500 class flange connection. N-butane was the most prevalent chemical in the pipeline makeup. The thermoset glass reinforced epoxy receives a not rated certificate for this chemical at 225°F. Greater than 20% swelling will occur with a greater than 50% loss in tensile strength. This confirms why the G11 delaminated. G11 is a type of GRE grade which is used for manufacturing these gaskets. And you can see the glass reinforced epoxy G11 had delaminated from the stainless steel core, and which led to the blowout of this gasket. A chemical treatment was also added to the media stream on occasions, and this treatment contained ethyl benzene, which has a non-rated rating at 70°F with the epoxy. Upon evaluation, we could see that much of the gasket was simply glass fiber with no epoxy left in the matrix. As this happened with the media in the line and started to migrate and permeate through the gasket material made of GRE. Once the epoxy was gone, the gasket lost its strength, and the 1636 psi line pressure pushed the seal into the weakened glass structure and created a blowout. Another scenario in the conditions that are changing in modern times is the high pressure and high temperature requirements. So the high temperature, that is the changing conditions are demanded for higher steam applications, and temperature has increased a lot over the years. As you can see, the temperature requirements for the well conditions are much higher than what it was in the past. So GRE does not have the high temperature capability, and homogeneous GRE does not have high pressure capability. Metal coated GRE should not be used in applications that are over API 10K, and fire safe glass reinforced epoxy or GRE should not be used in applications over API 5K. As we just saw, G10 covers very little of the potential temperatures in the previous slide and pressures that can be seen in today's pipelines. G11, another grade of GRE, which has a better temperature rating, is also slightly better with a temperature limit of 200°C, and it covers only a small portion of this graph. Moving on, we can see a case study of where how GRE gaskets fail in high temperatures. This is a live example to emphasize the risk of plastics being exposed to temperatures that they will not be comfortable with. This was a gas application at a Christmas tree. It was high pressures at 7,000 psi at over 330 degrees Fahrenheit. The gaskets were G10 with a stainless steel core. These gaskets were exposed to temperatures exceeding the rated value of G10 material. Now, the G10 glass reinforced epoxy, GRE, near the bore on both sides of the gasket was very dry and brittle, which is consistent with the epoxy binder being driven out of the glass fabric by the high pressure. Now, this leaves the G10 very weak and brittle and can allow the seals to creep, especially at these temperatures and pressures. The drying of the glass mesh, that is the absence of epoxy, became very less severe when it was away from the bore. That tells us the inner portions of the gasket experienced higher temperatures than the outer portions. And the upper limit of G10 is 302 degrees Fahrenheit or 150 degrees Celsius. So this was not the correct choice for this application, eventually leading it to a blowout. Another application where GRE has a shortcoming is its steam when it is introduced to steam. This was an actual gasket which was put into service, which was taken out of service after 34 weeks. This speaks volumes about the incompatibility of GRE in steam applications. Water combined with CO2 will produce carbonic acid, we know, and the epoxy in the GRE is incompatible with carbonic acid. So the carbonic acid wasn't the issue, but is incompatible with carbonic acid, but the carbonic acid wasn't the issue, but GRE is not compatible with steam. And this can be seen from the two images. G11 is rated at 200 degrees Celsius. So the 270 degrees Fahrenheit should not have been a factor, but the softening of the gasket due to the steam introduction and the volume loss led to a blowout, which is a real danger. A case study to prove this point is here. At GPT, we are lucky because we have a fairly large engineering staff who are able to review these failed isolation products and create a forensic report about it. We are also fortunate that we are part of Garlock family of companies, and Garlock has a tremendous number of analytics equipment in multiple laboratories. We are able to ascertain material component makeups, thermal degradation values, maximum temperature exposure, chemical attack, tensile values, change in tensile values, and so many other things that we can evaluate in our laboratories. We even have a functional test laboratory that can replicate the field conditions to make sure that our gaskets are going to work or our seals are going to work in the conditions that are out there. So in this case here, we have a 16-inch 600 class glass reinforced epoxy metal coat isolation gasket like the VCS that we had discussed before. The pressure was approximately 1440 psi and the temperature was 220 degrees Fahrenheit or 105 degrees Celsius. The media was hydrocarbons with steam and the application was a slug catcher. Analysis shows that the epoxy in the glass reinforced epoxy became hydrolyzed by the steam. Hydrolysis, as it is known in Greek term, hydro means water and lysis means to unbind. The epoxy chains were broken down under pressure and it literally got driven out of the glass matrix. This dramatically reduced the strength of the product and ultimately led to the leakage or blowout. In this case, the evacuation of the epoxy left voids in the body of the gasket. The voids were subsequently replaced by contaminants in the media of the stream, in the media stream, and that led to conduction and caused loss of isolating properties also. Another shortcoming of GRE is its chemical incompatibility when it comes in combination with sour content. If the media entering the gasket is not compatible with the GRE laminates, then there can be lots of types of failure. This is a study of glass reinforced epoxy's incompatibility to the chemicals in the media flowing through the pipeline, which can lead to chemical attack. In this case, G10 and G11 grade gaskets were exposed to sweet gas and sour gas for a period of 2 weeks. You can see from the bubbles forming on the gasket face that it appeared as though the G10 and G11 were being attacked by the sour gas. We performed mass change, volume change, and density tests on the G10 and G11 samples, and indeed they were both attacked and had significant changes in these three parameters by the sour gas that was introduced into the media while testing. This is a live case of how GRE will fail under conditions of chemical incompatibility in sour media. The temperature was 124 degrees Celsius, the pressure was 1180 psi, and it was a ring type joint flange, and the gaskets in this were only in service for 90 days. To really get a good understanding of exactly what happened to this gasket, let's have a look at a cutaway view of the gasket in the pictures at the bottom. The cause of failure was a combination of attack by sour gas and the effects of steam hydrolysis. You can see from the images that the idea of the gaskets were devoid of epoxy, extending all the way through, well, approximately 66% of the gasket. The high temperature water broke down the epoxy by breaking the crosslinks, and the hydrogen sulfide, as we know from other sour gas testing, that accelerated the breakdown in the epoxy by reducing the gasket's density and increasing the gasket's mass. Additionally, the hydrogen sulfide can dissolve into the water, and the carbon dioxide can as well create hydrosulfuric acid and carbonic acid, which can break down the glass fibers. So this domino effect led to a failure in just 3 months. GRE is not fire safe. You can see how a GRE looks like after it is subjected to a burning in fire. We have equipment to conduct road shows, and we have done some of these road shows in our customers' facilities at Abu Dhabi, Saudi Arabia, and India, and have in our quest to increase the awareness about lack of fire safety, the issues that the lines will face if they lack fire safety in the GRE non-fire safe isolation gaskets. Fire tests such as API 6FB, live roadshows, and history all proves this point. Now, which customer wouldn't want a fire safe product to increase their safety rating and records? Yet most of our sales testifies that the customers still buy non-fire safe GRE gaskets as the fire safe gaskets are very expensive for many. So when you subject a standard flange isolation gasket kit to fire, it tends to have, you can see here, it tends to have some failures. The gasket itself with its plastic laminates fail after a certain degree Celsius. So G11 would fail after 200 degrees Celsius, G10 would fail after 150 degrees Celsius, and so it leads to a fluid leak path. The other failure components are the isolation sleeve, which is also made from G10 or G11, and the isolation washers, which is also made from G10 or G11. Now, the contributing ones that the ones that contribute in these components to a loose flange assembly are the isolating washers and the isolating gaskets. So if you have isolating washers that are like, one of them is 3.125 mm thick, so if they fail on both sides in that thickness, and the gasket also fails, it can lead to leakage, and the fuel can add more fuel to the and the media in the line can add more fuel to the external fire, leading to a catastrophe. One of the examples is the storage tank explosion in Glenpool, Oklahoma, USA, where the excerpt from the incident report stated that crude oil at 550 pound was released from above ground piping, which was engulfed in fire. A non-fire safe isolation flange assembly in the piping failed because of the fire, allowing the pressurized crude oil to spray the surrounding area through the loosened flange assembly. So it is an example of how things can severely go wrong and can cost millions of dollars. That is many, many times higher than the slight premium that needs to be paid for a fire safe isolation gasket. Another big challenge with GRE laminated isolation gaskets is their thickness. The metal coat GRE isolation gaskets, due to the limitations of the then available technology, they were made thicker than the conventional gaskets. A metal coat isolation gasket is 6.6 mm thick when compared to a 3.25 thickness of a regular gasket. This leads to the need for a different approach of installation, and the flanges needs to be spread much more than the usual. In the bottom left image, you can see what happens when the flanges are not spread apart sufficiently and the gaskets could not slide in properly. They are hit by hammers and try to be forced their way inside the flange joint, which can lead to damage of the gasket as well as popping out of the additional seals that are laid into the gasket. When we are sometimes told that the gasket was damaged during installation and that the installation was done exactly as the manufacturer has recommended. When we ask to have the gaskets returned, we often see these large indentations in the metallic caused by the installers beating the gasket into the flange. Now, that is not a manufacturer recommendation. So the common 6.6 mm thick isolation gaskets will be a difficulty to install in pipelines that are designed for gaskets that are 3.25 mm thick. Flanges that are not perfectly parallel and are not well aligned will present even more greater issue. A case study about how this can go wrong is here. This is a live example of bad installation. 3 isolation gaskets were installed in the upstream side of a venturi meter. Not enough flange gap was created and the isolation gaskets was damaged during installation. Most high pressure isolation gaskets have retainers that are at least 6.6 mm thick. They typically have a seal that protrudes approximately about 5 mm more, and so a flange gap of at least 9 mm is necessary so as not to damage the seal or gasket. Interestingly, with this case, the downstream gaskets appear to have been installed first, and all 3 functioned properly. But when the upstream gaskets were installed, the space was very tight and limited, and that led to the tearing of the GRE as well as the popping out of the PTFE's additional seals. Now, what could be the ideal isolation product? We sent out invitations to corrosion engineers, integrity engineers, reliability engineers, and materials engineers of companies and users around the world and performed voice of the customers. And we got, based on the feedbacks that we had got from them, we have zeroed down to 5 essential points: fire safety at an economical price point, better chemical and thermal properties, thinner gasket for easy installation, high pressure capability, and low emissions. So these were the 5 points that we kept in mind when we were developing a gasket that is future ready. So this is the new product that GPT has introduced into the market about a year and a half ago, and it is called the Evolution. For the last 80 years, isolation gaskets have been a plastic laminate of some sort. As we have just seen, there are many potential failure modes with these plastic products. GPT has spent over 5 years researching the failure modes of GRE products and now proudly introduces this first isolation gasket that has eliminated any plastic or non-metal on the retainer of an isolation gasket. This is a 316 SS core gasket with a highly gasket retainer with a highly chemically resistant, durable, scratch resistant isolating coating. The ID is sealed by a Gylon 3500, which is a restructured PTFE seal and also highly chemically resistant. And the ID seal is backed up by a secondary seal, as you can see in that cross-sectional view, with a 718 internal C-ring that is also coated with a very chemically resistant coating. All coating surfaces are extremely impact and abrasion resistant, and we have subjected them to some severe testing and scratch testing to make sure that they are worth to be used in the pipelines and in the industry. The plastic handle also makes installation and removal easier. You can see it is a slight deviation from the regular gasket designs, and this makes the installation and aligning the gasket inside the flanges itself very easily. This innovative new solution is also 3.125 mm thick, which is in line with the general or the regular industry requirements of a gasket thickness. And it is API 6FP fire tested in multiple sizes and classes to make sure that it is fire resistant. Moving on, I was talking about having a tight sealing to make the new sealing options to be more compliant and more and better performing for emission requirements and bring down the leakage rate. Now, this new innovative design has several key attributes, and one of them is that it is extremely tight sealing. If we look at the sealability of Evolution versus a G10 on a stainless steel isolating gasket of the previous technology, you can see that in an EN 13555 leakage test, Evolution has a leak rate of about 1 × 10⁻⁻⁸ helium per second. That's about 1 cc of helium leaked over a 3-year period. Whereas the G10 laminated stainless steel isolating gaskets leak about 1 cc of helium every 3 hours. And many of the conventional gaskets out there, such as the spiral ones, are much more lower in performance than the G10 laminated on SS isolating gaskets. And you can imagine how much tighter the evolution is. The other requirement that was analyzed during our changing conditions slides was about the temperature requirement of the materials. GRE G10 is GRE G10 and G11, as we saw, has a temperature rating of 150 degrees Celsius. G10 is 150 degrees Celsius maximum, and G11 is 200 degrees Celsius maximum. Evolution is rated to 500 degree Fahrenheit or 260 degrees Celsius, and has shown very little degradation even at temperatures higher than that. It looks almost, the test was run at an ambient temperature when you compare these two graphs against a G10 material. When G10 becomes a molten mess by the time it reaches the temperature limits of evolution. You can see the G11 and the G10 compared to evolution based on the temperature ratings, as well as another important factor is the dielectric factor. Since these are isolation gaskets, the dielectric capacity is an important factor as it prevents the galvanic corrosion. Even the dielectric value of evolution is significantly higher than the homogeneous G10 and G10 with the stainless steel core. The same holds true for G11, which is also somewhere similar to the G10 in its dielectric values, and is rated at 800 volts per mil. Evolution, on the other hand, with its new coating, has a minimum dielectric value according to ASTM D149 testing requirements, dielectric testing requirements, as 1400 volts per mil. And that is the minimum rating. It has gone up to 1800 volts per mil in some of our tests. The other key factor here is that G10 and G11 will absorb moisture during a hydro test because they are permeating in nature, as we have seen in the previous slides. This significantly reduces the resistance values after a hydro test. I have seen test results ranging from 3 mega ohms to 7 mega ohms, and many companies in the specs limit the value at 10 mega ohms as minimum. And this can be a problem when you're using a G10 based gasket or a G11 based gasket after hydro test. Evolution, since it is a metal coat, it's a complete metal gasket and doesn't have any plastic laminates on it, doesn't permeate, and even after hydro test, the typical dielectric readings or the resistance readings are in the gigaohms range. Evolution is also much thinner than most high pressure isolating gaskets. The recommended flange gap for a typical flange should be 1.5 times the gasket thickness, which leads 9 mm spreading of a 6.6 of the flanges to make sure that you can install a 6.6 mm metal coat gasket. Now, if you are looking at a regular gasket thickness, that is way too high than the normal requirements. Now, if you look into the, as we already mentioned, the evolution gasket has no plastic retainers on it, and so it is much thinner in its construction. It has got a 3.125 mm thickness, which is in line with the industry regular practices or regular thickness of gaskets. And so you don't have to spread the flanges much more than what it is generally required. We also did sour testing for the new solution along with a new gasket type along with the G10 and G11 gaskets or materials. When we had immersed it in a sour gas media, the mass, volume, and density had changed significantly. This is a strong indicator that the product is being chemically attacked. The bottom line is that epoxy simply is not compatible with hydrogen sulfide. The gaskets were visibly affected by the hydrogen sulfide, indicating further that the gaskets were chemically reduced. Now, if you look at this slide, there are many graphs that are trying to tell the story about how G10 and G11 doesn't fare well in such kind of conditions, sour testing conditions. But if you, in a nutshell, if you want to know how it affects the three solutions, the tensile strength readings are given in terms of percentile decrease at the bottom right hand corner of this slide. You can see that G10 had decreased in strength about 69%. G11 had decreased in strength about 82%. But if you compare the evolution with it, it had very negligible change. There was nothing much that you can say that evolution will not be able to keep sealing even after the introduction of such media into the line. Another thing is another thing that we did to make sure that the evolution is chemically resistant to many of the conditions that GRE or glass reinforced epoxy G10 and G11 laminates are not, is that we have compared the chemical resistance to many other media conditions. And as you can see, we have introduced saturated steam, hydrazine, N-butane, hydrogen sulfide, carbon dioxide, hydrosulfuric acid, carbonic acid, ethyl benzene, and it gets a very good rating. It's a rating A. That means it is good to be used against these chemicals and will not be chemically attacked. So we made sure that the new solution is chemically compatible where a GRE normally fails. We have also tested evolution in high pressure tests. In this example, we tested in ambient temperature for 60 minutes of hydro testing. The worst performance we had seen was 28,000 psi when we tested 4 samples, and that also was not because the evolution had leaked, but the flanges were lifting off. Even the 32,000 psi and 36,000 psi are all leakages when flanges started lifting off at such high pressures. We need to do much higher with higher rated flanges to see what would be the actual pressure conditions that evolution can hold on to without a blowout. G11 or G10 with a metallic core will leak or blow out at between 15,000 to 20,000 psi when it is subjected to pressure testing. We have another important thing to talk about is the coating, since people will be unfamiliar with the coated isolation gasket. When we started evaluating coatings for potential use on this isolating gasket, we looked at several tough coatings available in the industry, like the 3M coatings, the PTFE coatings. So many coatings are available out there. The 3M coatings proved to be one of the toughest in the industry. And as you can see in this graph, the ASTM 2197 scratch resistance test, that was one of the tests that was that all the coatings that we had evaluated was subjected to. And in this test, we run a 2 kilogram load tungsten stylus, which keeps moving up and down till it scratches the coating away and it hits the base metal. And this stylus is connected to a voltage supply. So the moment it touches the bare metal, there is a resistance breakdown. And the 3M coatings, which are good among all the other coatings that is available in the industry, they had 99 revolutions of the stylus moving up and down before they broke down. We had developed, when we had first developed this coating, that you can see the readings of the graphs in the red color on this graph chart. We have put it as old evolution. We tested it against these other coatings, and it took about 250 revolutions before it failed. But you can see another graph in brown color. It was the second edition of this coating, which we improved it further with more additives and all to make it more strong and be more resistant to the site conditions. And you can see that that new combination is much more better than the old combination, which was already better than all the coatings that are available in the market. It is 10 times more stronger than the older coating. So in short, this coating that has been used on this gasket is very, very scratch resistant and very, very highly durable than any other coating that you have seen right now available in the market. Now let's just recap all the cases we had initially seen where the GRE isolation, glass reinforced epoxy isolation products had failed, from the perspective as if we had installed an evolution in each of those same applications. In the first case, evolution does not allow permeation and will resist hydrolysis and will survive in that application. Also, evolution is chemically compatible with N-butane and ethyl benzene and would not have been chemically attacked. In the second case, Evolution has a much higher operating temperature rating than either G10 or G11 and would have worked well in an application requiring exposure to higher temperature. The third case involving steam, evolution resists hydrolysis by steam and would have survived that application too. The next case involves exposure to sour gas, and since evolution is chemically compatible with the levels of sour gas that was present in this application, it would have performed well even in this application. Since evolution is fire safe and tested to API 6FB 3rd edition fire test requirements, it would prevent a catastrophe or emergency in the event of an external fire by containing the flammable media that is in the line within the line. In the last case, evolution is less than half of the thickness of most plastic isolation gaskets out there and would have been much easier to install. Once again, if we revisit the 5 major requirements of an ideal isolation gasket as put down by the VOCs that we had gathered from the industry, we can see that evolution is specifically designed to meet all these needs. It provides fire safety at an economical price point, has much better chemical and thermal properties compared to a GRE or a glass reinforced epoxy lined gasket, is thinner to facilitate easier installation, has high pressure and capability, and has very low emissions. And this one product eliminates the need for homogeneous GRE gaskets, steel reinforced GRE gaskets, fire safe GRE gaskets, and PTFE ID seal GRE gaskets. It is truly one simple solution available to take care of all the requirements that the industry poses now and in the future. So exactly what are the specs on this new product? It is a 316L SS stainless steel retainer that has been fully encapsulated in a proprietary coating. It is also a primary sealing. It has also a primary sealing element made of Garlock's Gylon 3500, which is a re-engineered better PTFE design, and has tremendously reduced creep and core flow characteristics when compared to a regular PTFE. There is a secondary seal which is made of Inconel 718, which has great recovery characteristics and is also the seal that is going to prevent any leakage during a fire. The Inconel seal is also fully encapsulated in this coating. The color of the retainer is dark brown with a tan primary seal. The coating is approximately 0.010 inch thick, and the gasket is currently rated to minus 50 degrees Celsius as the minimum temperature and 260 degrees Celsius as the maximum temperature. We are doing tests for much lower temperature to see how this gasket can be used for cryogenic LNG applications. The sizes available right now are 1/2 inch to 36 inch, although engineering is working on larger sizes offerings, and we should be able to offer 48 inches before too long. The pressure offerings are 150 class to 2500 class for ANSI class flanges, and API 6A flanges from 2K to 5K, although engineering is right now working to offer for API 10K and API 15K applications also. We are extremely excited to offer a design that eliminates so many issues that the industry was facing otherwise from GRE isolation gaskets. And we are confident to say that we have a solution that can perform well in the oil and gas, not only in the oil and gas applications that are prevalent today, but also in the years to come, and is future ready. So that is the presentation on today's topic, and I hope you have it was informative for you, and we are happy to take any questions and answer them, so that we can discuss further about what this solution is and what the industry is facing right now. Once again, thank you to Oil Review Magazine for facilitating this presentation and this platform to talk about our product, as well as the conditions that have led to designing it. Thank you.
Thank you very much indeed, Rony. That was a really fantastic and in-depth presentation, and I'm sure it gave us all a real understanding of the changing and increasingly demanding pipeline conditions in the region, the resulting effects on flange corrosion and mitigation, and the need for improvement in gasketing and sealing. We heard about the important role of flange isolation kits, shortfalls of GRE-based isolation gaskets, and why innovation in this area is long overdue. And finally, we heard about GPT Industries' fully coated evolution isolation gasket, and how it specifically addresses those 5 customer requirements which you highlighted. And I thought particularly were instructive were those live cases that you showed where failures could have been avoided had the evolution isolation gasket been installed. So now let's open the floor to questions, and please do keep your questions coming in because we do have a little bit of time. Okay, so here's one for you, Rony. It's about affordability, basically, and how the cost of evolution compares to the G10 and G11 products.
Yeah, so as I was talking during the presentation, one of the requirements from the customers was having an isolation product which is fire safe, but not having the premium of fire safety built into it. So customers were not buying fire safe isolation gaskets in the past because it was much higher in cost when compared to a regular isolation gasket, which itself is expensive than the regular gaskets or sealing solutions. This has its own reasons, because the flange isolation gasket doesn't come as a gasket alone. It has got a kit to accompany with it, and that kit has got sleeves and washers. Everything is offered as a set to the end user. So talking about the price of the economic part of this gasket, so if you figuratively speaking, if you are looking at a gasket which is say X times X price for a regular isolation gasket, non-fire safe one, a fire safe one is like 3 times that X price. But in the case of evolution, we are offering it at a price of the X. That is I'm just speaking like that because I can't give you any figures right now, but it is offered at the same price of a non-fire safe regular isolation gasket kit.
Great, thank you very much. A question about H2S. What materials should be used for high H2S in place of GRE? I think you may have addressed that that question, but I don't know if you wanted to comment any further about GRE and H2S and how common failure is in that respect.
Okay, it's a good question actually. So H2S in itself, GRE is inert to many chemicals, and H2S in itself alone may not affect detrimentally up to a certain percentage, though a high percentage of H2S can obviously degrade or bring down the volume and density content of GRE material, as you saw in the previous slides. Now, but in the media, or the media in the pipelines are not just H2S. They are in combination with several other hydrocarbon units, as well as carbon dioxide and many other combinations, especially steam, if it is there along with H2S. That is another big factor that can cause to the degradation of GRE much more, or accelerate the degradation of GRE much more than a regular H2S, normal plain H2S solution could do. So as we have seen, steam combined with H2S, it can just break down the epoxy layers in the gasket, leading to a blowout. Even any kind of carbonic acid, sulfuric acid formations at a certain temperature, high temperature, can just cut through the GRE material and permeate more than how much it naturally permeates and create a blowout. So H2S in itself, H2S in combination with other media contents in the pipeline creates a very big detrimental effect, posing a challenge for GRE to seal in such conditions.
Great, okay, thank you. Another question, and you did highlight some failure issues, of course, but how common are those issues, do you think, that you're seeing with failing GRE gaskets in the industry?
So, yeah, so we have seen many issues over the years. Many of them basically are GRE gaskets are quite a good gasket itself. and the industry has seen their advantage over the years. But it was, if you take it, it was suitable to a certain period of time. The technology back then and the kind of wells that we were drilling and the kind of media that was being handled was okay with the GRE laminates that has been there in the that has been used for sealing. Now, it doesn't say that GRE is going away anywhere. GRE has its own credibility and it can still go on for some more time. But if you look into the future, things are changing at a very rapid pace. Fracking, and then there are a lot of much more deeper drilling, higher steam temperature and pressure is being put to extract oil from hydrocarbons from the very not so easy kind of wells, so our positions. So in that condition, different technology is required. So GRE in itself, we have seen failures in some certain cases, like as we had highlighted right now, where say a steam content with high H2S content, high H2S content has cut through the body of the gasket. Then because of its higher thickness, which is not possible to reduce at this present time, with a GRE gasket, we have to maintain that thicker gasket for high pressure content. We have seen that when people install it, it poses its own challenges. So you can't spread a normal flanges apart beyond the regular gasket thickness requirements. And installation is one of the critical factors which leads to blowout or leads to failures of sealing solutions. If you don't install it right, you are going to face problems in the future. And that's one reason where I was talking in the beginning slides, that we as a manufacturer also take preventive measures, proactive measures to train the personals at site or in customer facilities to from customer side, to give them a knowledge about how to install these kits in a better way and help them prevent any kind of failures due to wrong installations. And one of that program that we have is called GFIT, GPT Flange Isolation Installation Training, Flange Installation Training. And that is also available with us, where we proactively give customers a training to stop failure of GRE gaskets if they are not installed properly. The new gasket, as I showed you, has got a handle to make sure that it is aligned properly. The installation is much more easier, thinner construction. We have covered that kind of problem. So there are many more examples like these live cases that we have shared here. They are just 4 cases right now. Fire safety is an issue, though the GRE has got an inbuilt fire safety seal with the GRE gaskets. But they obviously, if you look into that price factor, when you have that fire safety built into it, it drives the price much higher. We cannot give economical solution with a GRE laminated fire safe gasket, because there are lots of things that have to be factored in while manufacturing such a gasket. With the Evolution, it is much more easier design, and it has a much more leaner manufacturing platform to make sure that the cost to build this gasket is much lower, and price can be made more economical for the customers to have a fire safe gasket.
Great, thank you very much. Okay, another question. What is the material spec for the isolating washers and sleeves on the bolts?
It's G10 and G11. With the new Evolution gasket also, we are providing sleeves made from G10 and G11. As I was showing about the fire safety on the fire safety slide, when fire affects a flange isolation kit or a flange with a flange isolation kit installed in them, 3 components fail: the isolating gasket, if it is not fire safe, the sleeves, which are made from GRE or GRE laminates, and the washers, which are made from GRE also. Now, the washers and the gasket, if they fail, they reduce in thickness, and they can add or they can contribute significantly to the leakage of media through the flange sealing, through the flange joint. Now, if you look But if you look at it, the isolation sleeve doesn't matter, doesn't contribute to the leakage of the solution. Now, that's why we have kept the sleeves as G10 and G11 in the evolution gasket kit also. But the washers in a fire safe kit is metal cored, and they are all or metallic washers on both isolating and backup, but they are coated with a dielectric coating, just like how we have coated the evolution gasket. So it is a metal washer, two metal washer, both are coated in the dielectric substance to make sure that the washer doesn't get burnt off during fire. So it will not contribute to the fire. I think I have covered that point of how the materials are being selected. So evolution comes with a G10 and G11 sleeve and metal coated washer system, dual metal coated washer system. And we spoke about temperatures above 200 degrees Celsius, where obviously we need to change the material of the sleeve and the washers also. And so we have a mica sleeve combination about 200 degrees Celsius with the evolution gasket, and mica washer with stainless steel inside, substrate inside, and stainless steel backup washer. So that is the arrangement with temperatures above 200 degrees Celsius. Below 200 degrees Celsius, dual metal coated washers and G10 or G11 sleeves.
Great, thank you. Maybe just time for one or two more questions. Another one, can this isolating gasket be used in place of monolithic isolating joint for pipeline applications? And how efficient is it in terms of absorbing pipeline loads induced?
It's a good question. So in the past, monolithic isolation joints, so GPT manufactures both flange isolation kits as well as monolithic isolation joints, and as a fully isolation products manufacturer and supplier. But monolithic isolation joints have their own merits and demerits. Flange isolation kits have their own merits and demerits. If you compare to MIJ, yes, it can handle a much more dynamic loading on the pipelines, and they are more efficient in terms of not having any nuts and bolts in them. The lesser number of, the joint is fully prepared in a factory condition, and so you are sure about what are the readings that are already gone in while installing that flange joint. Now, FIKs had its own shortcomings in those days, but it facilitated opening of the flange for maintenance. Wherever you needed to break up the flange over a period of time, that was the only solution available. But today, with this improvement in the technology, being fire safe and very tighter sealing and low emissions and all those kind of things that are being achieved by the new gasket solutions, especially the evolution, you have almost all the desirable factors that you get in a MIJ. It can handle those loads. It can handle. It can be easier to install, and as you saw in that EN13555 test, it exerts a very high tight sealing even at a very low bolt load. So the M and Y values are much lower than any regular gasket, and even lower than the other isolation gaskets that are available in the industry. The sealing capacity is, as you saw, it's a class A rated as per Shell requirements. So 10⁻⁸ helium leakage per cc of helium leakage every second. That is like, as I mentioned, 1 cc of helium leaking over a period of 3 years, which is very high when compared to what is available in this industry in terms of regular gaskets as well as all the other isolation gaskets. So the desirability what MIJs had in the past is almost taken care of with the new offerings. Obviously, we still can't deny the factor that MIJs are one complete joint with no bolted connections or anything, and it can be used for underground buried applications with no fuss of ever taking it out or changing them, and can be kept for a longer period of time. But FIKs give you that flexibility of opening up the flanges at regular intervals and doing the maintenance.
Great, thank you. One last question then. What code are these gaskets designed to? Would they be installed on normal B16.5 flanges?
Yes, nice question. So these gaskets, they are designed to the flange phase or the flange spec. So as you said, ASME B16.5, if the flange that is required to be sealed, they are designed to ASME B16.5 flange dimensions. If it is an API flange, it will be designed to the API 6A flange dimensions, or whatever flange specification that you have at site. Now, you might be asking why it is not following the gasket specifications that are laid down by ASME. Now, there is a hole to it, because if you look at the gasket specifications like ASME B16.20 or 0.21 or for metal and non-metallic gaskets, what they lay down is like for a spiral wound, it has to protrude, the OD of the gasket has to protrude a little more into the PCD ID of the nut of the bolts, which makes it self-aligned while installation. Now our gaskets, we cannot design it to that OD because it comes with a sleeve on the stud, and the sleeves have sleeves are a bit thicker, like 1 by 32 inch of a 1 by 32 inch thicker. And so it has to be considered the ID plus that 1 by 16 inch sleeves on both sides of the bolt when considering the outside diameter of the gasket, so that the gasket OD does not crush through the sleeves and break down the isolation between the studs and the gasket itself. So there are certain limitations which doesn't allow us to design these gaskets to a gasket specification, but obviously we design it to the flange specification, and all these gaskets have been supplied in the past for almost 45 years on the flange specifications like ASME B16.5, B16.47A or B for the bigger sizes, API flanges, DIN flanges as per what the customer requires. And then we have standard dimensions laid down for all these flange arrangements. So you need not worry, you can just install them if you give us the flange specifications, that's it.
Great. Just one more final question, if you don't mind, Rony. What do you mean when failures occur in a typical gasket? With Evolution, you mentioned that there are virtually no failures. And is this based on simulations? How has it been tested?
You mean the failures that we had talked about, or generally failures on all the gaskets?
In typical gaskets, when failures occur in typical gaskets.
Okay, so
yeah,
sealing solutions, they are subjected. They are very. If you look at it, they are very. They govern a very small price or premium when compared to the other components in a pipeline, but they are not unimportant as per their pricing, because sealings, as we have seen, if they break, they break, and they can contribute to a bigger catastrophe in a critical situation like a fire or emergency. So it is very important to make sure that seals are compatible to the chemicals that are in the pipeline. Seals are much more tighter sealing if it is a critical environment polluting kind of media, or which can add to the greenhouse requirements, greenhouse emissions. So seals have to be selected with carefully to make sure that it performs to the line or the place that it is going to be installed. Now failures occur if it is not selected in the right manner. One of the ways of failure is if it is not compatible to the media. But before even happening such failures, the main failures happens when you are using a untrained personnel or people who are not very knowledgeable or not knowing how certain seals have to be installed. Several types, the sealing material governs the ways of how to install them. PTFE or a non-metal sealing solution needs a different way of sealing than a metal-based sealing gasket. An isolation gasket requires a different kind of sealing methodology than a regular metal or a non-metal sealing, because it has got sleeves and washers in there. You have to make sure that the washers are installed in the right direction to make sure that they are achieving the purpose that they are built for. So there are so many kind of failures that can occur if you are not selecting the seals in the right manner, if you're not installing them properly, if you're not torquing them properly, and then if you have not selected them as per the media content in the pipeline. After all this, the fire safety is another factor. You have to put that emergency factor in your mind, because say if your line is carrying LNG or any kind of hydrocarbons that are going to be highly inflammable, then you have to make sure that the seal is also fire safe. And in the event of an external fire, the media is not going to leak into that fire itself and add fuel to the fire. Yeah. So these are the conditions where a seal can fail, and these are the things that you need to keep in mind when you have a seal.
I think the question as well was, how has evolution been actually tested and proven to be resistant? Has it been tested through simulations, or how is it actually being?
Yes. So yeah, that's I missed that point. So yeah, evolution has been tested to almost 48 different kind of testings that we have seen in the sealing industry, and more than what normally a sealing industry does on its gaskets, or a sealing manufacturer does on its gaskets. So there are the regular hydro tests, the dielectric test for an isolation material. Then there are other kind of APIs, PR2 cyclic loading tests, and cryogenic application tests. There are so many other tests that you can line them. We have even done the HOBT, hot blowout, cold hot blowout, sealing tightness testing. All this outside our factory in Amtech laboratories. We have done the fire testing in Yarmouth laboratory. We have done testing for sour content in Elements laboratory. So we have done like 48 different tests to make sure that evolution is complying to many of the requirements of the industry and is future ready and won't fail where regular seals are failing. One of the other major tests that we have done is Chevron FET analysis, fugitive emissions testing, and the figures there was like evolution was Chevron FET testing requires 100 parts per million as minimum as the minimum leak emissions of that gasket. The evolution was reading at 35 parts per million at ambient at higher temperatures, and at ambient temperatures it was just 2 parts per million. So we have done so many tests to make sure even the coating, as I was showing, there are many bar graphs, but many more tests have been done inside the plant as well as in third-party laboratories to make sure that this gasket is compliant and to many of the conditions and requirements of customers and won't fail where the regular seals are failing.
Great, thank you so much, Rony. So it just remains for me to thank GPT Industries and Rony for this fantastic presentation. And please, if anyone does have any further questions, do get in touch with GPT Industries on the contact details on the screen. So thank you very much indeed to everybody, and thank you to you, our audience, as well. Thank you very much, and goodbye.
Thank you. Goodbye.